So good evening, everyone, and welcome to the fourth LatentView RBCDSAI Colloquium series. And so we are very thrilled and honored to host Professor Peter Stone from UT Austin. And I can read a little bit of Peter's standard bio, uh, which all of you already seen. So Professor Peter Stone is the David Burton Jr. Sentinel Professor and Associate Chair of Computer Science, as well as the Director of Texas Robotics at the University of Texas, Austin. And he's also heads the Executive Director of Sony AI in America. And so Peter has won multiple awards, including the Texas System Region's Outstanding Teaching Award, as well as the Fellow of multiple academies, the AAAI Fellow, IEEE Fellow, the American Association of Advancement of Science Fellow, ACM Fellow, everything. There's one interesting connection now for Peter to India, is that when he was awarded the prestigious Ichigai Computers and Thought Award, given to the top AI researcher under the age of 35, he actually received it in India. So he had come down to Hyderabad for Ichigai and had given his award lecture there, and he actually so that's one of his connections to India. And of course, he has guided a lot of amazing Indian students who are doing great work around the around the globe now. And so I know Peter for a while now. And one of the things is I always hold up Peter as an ideal mentor, the way that he, the way he, even today, he keeps track of all of his students, where they are and how much he helps them out. And I mean, I try to kind of aspire to be like him in terms of mentoring students. But thank you, Peter, for being an inspiration. And thank you again for agreeing to talk at our colloquium series. Over to you.
My pleasure. Thank you very much for the kind introduction. Yeah, that was very generous words. I do remember my trip to India very fondly. So I was there for the Ichigai 2007 conference and did travel around for 3 weeks through the country with my wife and had a wonderful time. My other, and as you said, I have mentored several Indian students. One of them is now Shivaram Kalyanakrishnan, is now a professor at IIT in Bombay. Some of you may know him. In any case, thank you all for being here, and thank you, Ravi, for inviting me. What I'm going to do today is give an overview of things that I do in my lab. I actually touch on a lot of different research directions, but then go on a deep dive on one or two areas that I think might be of interest. So there'll be sort of something for people who want sort of the breadth, and then a couple of items for people who want to get a little bit of technical depth. But there'll always be a chance to pop back up. Just as a start. It is actually very exciting times at UT Austin right now. I'm not there physically with you in India. I hope I will be someday. I also hope some of you will get a chance to come and visit us here at UT. We just founded a new machine learning laboratory that was prompted by the awarding of a very prestigious new National Science Foundation Institute for the Foundations of Machine Learning. Adam Clivens is the director of that. And then I direct a new center on Texas Robotics, where we had a ribbon cutting on a beautiful new space last October. This is before we moved the robots into it. This is actually 2 old gymnasiums that they've opened up for robots to roam around. And we've now filled it with some fantastic colleagues in research. There's now many core robotics faculty across several departments. When I first got to UT Austin, I was the 3rd roboticist. We now have 16 fantastic faculty in core robotics, people who publish at ICRA, IROS, and RSS. So as I said, I do a lot of different things in my lab. The question that ties them all together is, to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? And so within artificial intelligence, we publish in a number of different areas: in autonomous agents, multi-agent systems, robotics, which will feature heavily in this talk, and also in machine learning, and especially reinforcement learning. Along with Ravi, the two of us have both been working on reinforcement learning for much longer than it's been a popular research topic. but now it's really it's come into its own, and I'll talk a little bit about some of our contributions there and the kinds of things we're thinking. In my lab, we do both sort of what I call bottom-up research, where we start from foundational problems and contribute new algorithms, and more top-down applications-driven research. And it's difficult to give you a sense of all of the sort of foundational algorithms we work on, but I can very quickly give you a sense of the application domains that inspire us. One is robot soccer, and so this is a clip from a RoboCup robot soccer competition from several years ago, where the robots were fully autonomous. They have to sense, decide, and act without a person in the loop. I'm now the president of the RoboCup Federation, the International RoboCup Federation. I'll say a little bit more about that shortly, but this is another video from the finals, actually, of a competition several years ago that my team ended up winning. My robots were the ones with their hands behind their back. These are the SoftBank Now robots, where both teams have the same hardware. So it's about who can program the robots to see the ball, to walk more effectively, which will come up much more in this talk in a second, and to do teamwork. Here you see our robot going in on a breakaway in one of the competitions. This one we ended up beating a team from the University of Bremen in Germany. This has been a perennial powerhouse in the competition, but we won this game 4-2 and went on to win the competition. I'll say a little bit more about robot soccer shortly. Another motivating domain for me is what I call general purpose service robots. This project called the Building Wide Intelligence. In this project, we try to have robots like this one in the top upper left corner, just wandering around the building and interacting with people. This particular research video is about some grounded language learning that I did with a colleague, Professor Ray Mooney, one of his students, Jesse Thomason, and my postdoc, Shuqi Zhang, who's now a faculty at SUNY Binghamton. The robot needed to, over a week-long experiment, people were able to type to the robot in natural language, whatever they wanted to say, things like, deliver coffee to this person, or go take me to Peter's office. And if the robot didn't understand, it would ask questions until it understood what the first sentence meant. And then it would use that as a training example to improve its understanding of the way people use syntax and semantics and language. And at the end of a week became much more effective at understanding people's commands. But this is just one project in this overall goal of having these robots be always on. You don't have to ask me for a demo. If you come to my lab, this robot is usually wandering the hallways, interacting with people. And then also the last application domain that that has driven, been a driving factor for my research, so to speak, is autonomous driving. We did have a car in the DARPA Urban Challenge in 2007, the one shown here in the bottom left. I'm not going to show a video of that. You've all seen autonomous cars driving at this point, but we do also still think about what will the roads look like when all the cars on the road are autonomous, or maybe most of them. This is a video that that my student Kurt Dressner created back in 2004. So a long time ago. And what's going on is the cars that are in yellow don't have a reservation yet, but the ones that are in white have called ahead to get a reservation in space-time through the intersection. And they're able to pass through with a guarantee of no collision with the other cars once they have that reservation. One of the first times I showed this was at in a sort of large lecture, was the talk in India, and people told me, well, that's what all the intersections look like here. But the difference here is we can at least guarantee that if the cars are following the protocol, there won't be any accidents. And this is also has spurred research on questions of what will happen if we move to multiple intersections and many more cars, and if there's pedestrians and bicyclists, things like that. So I could give an hour-long talk on any of these application domains, or any more on several different other sort of foundational issues. What I've decided to do for you today is to give a brief, deeper motivation about RoboCup, the Robot Soccer World Cup, just a few more slides on that, and how it motivates some of the challenge problems we work on in my lab. And then I'll talk about some humanoid robots. And I talked about, the theme of this talk is machine learning for robot locomotion. So we'll first talk about humanoid robots. And I'll introduce a method that we call grounded simulation learning. And I'll also talk briefly about some of the connections to some foundational results in off-policy reinforcement learning. And then I'll move on to some algorithms that we've used with that we've developed for wheeled robots, especially navigating through tight spaces. And a class or a family of algorithms that we call Adaptive Planner ParameterLearning. Okay, so to dive in, so RoboCup Soccer, that we have a grand challenge, which is by the year 2050 to beat the World Cup champions on a real soccer field. And this is, a big ambition, of course. People always ask, is it possible? There was actually a BBC news article about this last week where I was interviewed. We always say, I tend to say that it's not something I would, bet a lot on. There's some really big challenges to be able to make that happen. On the other hand, I wouldn't bet a lot against it still. 30 years is a long time, and we've been making a lot of progress. And a way of seeing that is to see some differences between what it looked like in the early years and what it looks like now. First, some of the features as a challenge problem. It does allow for easy entry. If you want to get involved in RoboCup, I very much encourage you to. There's lots of different leagues. It's allows for sort of dealing with closed loop systems at every stage, and allows us to study lots and lots of different research issues. In terms of the progress, this is what RoboCup looked like in the first years in 1997 and 1998. 4 different leagues. These aren't all my robots. It's participants from the different teams. In the top left were early IBO robots in the standard platform league. The top right is the middle-sized robots where they use a real soccer ball. The small-sized robots in the bottom left and the simulation in the bottom right. They're all somewhat have different technical challenges, but they were all fully autonomous. No person in the loop. Nobody giving any kind of input. They don't look very good. It's sort of painful to watch this. The robots are falling over. They're moving slowly. But then if you jump ahead several years, and still 15 years ago from now, you see a lot of progress of the robots moving much more quickly. There starts to be some teamwork, some passing. They're starting to shoot from farther away. The bottom right is the beginning of the humanoid league, where there was just a penalty shot competition that year. But if you if you look at RoboCup videos from recent years, you start to see even much big improvements from those as well. So it's really been exciting to see. As I said, I'm the president of the RoboCup Federation. It's a very large worldwide community that has these sort of common objectives. The league that my team has actually been doing very well in over the past decade or so is the 3D Simulation League. So this is when you can enter. You can enter without any hardware. There's sort of like a sort of video game kind of interface, except each robot is controlled by a completely separate program, and they have partial information. There's a physically realistic simulator, so there's gravity involved. It's hard to get them just to stand up, to walk, to kick. And then there's the strategy involved. Our team has won this competition 9 of the last 10 years using a form of hierarchical machine learning as sort of our secret sauce. This is my student's favorite highlight, where the robot kicks the ball through the legs of the opponent into the goal. But it was Patrick McAlpine, who's now at Sony AI, who was a leader in this team, and now we're continuing to follow up on his work. Finally, I did say that by the year 2050, our goal is to have humanoid robots that can beat the best soccer players on a real soccer field. Every year since 2007, we've had the winners of the middle-sized league play against the some amateur soccer players, including myself and some of the other trustees of RoboCup. So far we're still able to run circles around the robots and score goals, but every year it does get a little harder, and we are seeing that there's definite improvements going on in the development from year to year. I should also say that the reason I'm telling you about this is that as you'll see in this talk, the challenges that come up in RoboCup are inspiring of much more of sort of basic fundamental algorithms and sort of research breakthroughs that we make. RoboCup isn't just about soccer, and so it's important to know that there's also a league in RoboCup called RoboCup at Home that works on general purpose service robots and works on tasks like this one, where a robot needs to navigate through an apartment, find the trash can, take off the lid, pick up the garbage and take it out. There's also and there's other tasks, things like serving serving food to people, putting away groceries, that involve interacting in natural language, that involve manipulation. And there's both a standard platform league that uses this Toyota HSR robot, and there's a open league where people build their own hardware. Then there are other leagues in RoboCup as well. There's a disaster rescue league. There's RoboCup Industrial, which is sort of more workplace kind of tasks. And there's RoboCup Junior that introduces high school kids to robotics. One of the most challenging tasks in RoboCup at Home is this one, where a robot has to go into a restaurant that it's never been in before, where there's a table set up with a bunch of different products like Pringles and a Coke can or Sprite, and then it has to go find a customer that's waving, go up to them, ask what they would like in language, spoken language, understand them, go pick up the right object and bring it to them. And so, these are really inspiring challenges, and I really hope that some of you who here in the audience will go investigate a little bit more about RoboCup and join us. We just finished a very successful virtual event because of the pandemic in 2021, and then next year's competition is planned for July in Bangkok in Thailand. Okay, so that's the sort of a little bit of motivation. RoboCup as a source of challenge problems, and now I'll tell you about some of those problems that have emerged for us and some of the solutions that we've developed. So first of all, in this theme of machine learning for robot locomotion, as you saw, we participate in one of the leagues where you have to get humanoid robots to walk, and of course, whenever if you have humanoid robots or any kind of robots in a competitive situation, the faster they walk, the more of an advantage they'll have. And it's very natural to say, can we get these robots to learn, maybe for different carpet surfaces, or to be able to improve their performance. And so with two students, well, many students, but featuring Patrick McAlpine and Josiah Hanna. I've already mentioned Patrick. Josiah is now a faculty member at University of Wisconsin-Madison. We'd love to be able to do this learning directly on the real robots, but there's a lot of reasons that's challenging. It's not very data, many of the learning methods you want to use aren't very data efficient. So you have to, pick up the robot when it falls over, the robots can break, things like that. So it's very tempting to say, let's just learn in simulation, where you can do thousands of trials in parallel. The problem, and you can just sort of set up a situation like this in the simulator and have the robot practice dribbling the ball or walking fast or whatever you want it to do. And you can learn using CMAES or off-policy reinforcement learning methods or PPO to learn fast skills or that work really well in the simulator. But then if you deploy them in the real world, this is something, a skill that we developed in that simulator. We try to put it on the real robot, and you can execute it, but it doesn't look very good. The robot falls over because inevitably there's differences between the simulator and the real world. So this motivates, I think, one of the most important current open research directions in machine learning and robotics, which is called sim to real, which is how can we take methods that are efficient or effective when learned in a simulator, or when using a simulator to do the learning, and get the results to work in the real world. And so, diagrammatically, you have, in the normal reinforcement learning setting, you're trying to learn some policy that takes in states and outputs actions, and the difference between, and then there's some reward signal that also comes from the environment. And you can execute the same policy in both the real world and the simulator, but they'll have different effects. And that's so the red arrow is different from the green arrow. And there's a number of different ways to deal with this. There's one popular method is to inject noise into the simulated environment, so you learn a more robust policy, and then hope that the noise that you've learned to deal with in simulation envelops the noise that you would see in the real world. And there's several successful approaches in that direction. And another sort of general method is to go the other direction, to get some real data from the real world and use that to make your simulator more real or more grounded. And that's what I'm going to talk about today is in this second class of methods. And what we've introduced is a method called grounded simulation learning, which is an iterative method. It starts from the premise that we're never going to get a perfect simulator. that the simulator is inevitably going to be different from the real world. All we want to do is try to get the simulator to be good enough in the region of policy space that we're currently searching. And so how we do this is we get some real world executions of a starting policy in the real world. We gather some real world state action trajectories from that. Then we use that to, for the most important step here called grounding the simulator, which I'll explain over the next few slides. This is where we make the simulator more like the real world. Then we take the grounded simulator, improve our policy using standard learning methods in the simulator, take that improved policy, and then repeat the loop. And what that means is that we're now going, we're going to change the simulator again to be better, more closer to being accurate for our new policy. It might now be less accurate for the old policy, but we'll sort of keep doing this iteratively. And so I said the important step here is the simulator grounding. So how does simulator grounding work? What does it mean? So you could imagine just learning a completely new simulator from scratch. But for any kind of really complex environment, that's not going to be practical. You may have already a really good simulator like that RoboCup simulator that I showed you, and it might even if it's open source, which the RoboCup simulator is, it might be complex enough that it's going to be difficult to go in and create a gradient through that simulator and try to improve it from first principles. So what we're doing instead is we introduce a method that actually works with the simulator as a black box. So the simulator stays the same. Instead, what we do is we learn a wrapper around it that transforms the actions that come out of your policy before sending them to the simulator, with the goal of making it so that the transformed actions have the same effect in the simulator that the original actions have in the real world. Okay, so just to expand on that a little bit, we're going to learn an action grounding function G that takes actions as input and then produce a more realistic and then replace those actions with new actions that produce this more realistic transition. And what do I mean? And so how do we do this? How do we learn an action that has the same effect in the simulator that the original action had in the real world? We do this by composing a forwards dynamics model of the real world. This is a function that takes the current state and the action and predicts what next state will result in the real world. And we combine that with an inverse dynamics model of the simulator, which says, given this state that I'm trying to get to from my current state, what action do I need to execute? And so in our case, think of the actions as being like the joints, torques to the joints, right? So, or position, if we're doing position control, position commands to the joint. So if my current joint's at 90 degrees and I want to move it to 180 degrees, in the real world, if I say move it to 180 degrees, it may only move, in one time step to say 100 degrees. But in the simulator, if I tell it to go to 180 degrees, maybe it goes almost all the way there to like 170 degrees. So I now want to say, okay, when I want to move it to 180, that's the command that I would send to the real world. I want to replace that with a command that says, say, move to 115 degrees in the simulator, which will get almost there. It'll actually get to 110 degrees, which is the same that would happen in the real world. So that's how you can think of this. So then we learn this grounding function. We then put it, connect it, wrap it around the simulator, and then do learning within the simulator. The two components here that are important to learn are the forward dynamics model of the real world and the inverse dynamics model of the simulator. We can train those using a deep neural network, as is the fashion these days, based on a relatively small number of real world trajectories, because they all have lots of time steps. This is robot control, so 10 to 30 times a second you're controlling the motors, and so even in a 30-second trajectory you get lots of different time steps. And we can take state actions and predicted next states as the labels for the forwards dynamics model, state and predicted next state, and this and the action that gets them that does that transition in the simulator for the inverse dynamics model, and train them together. So this is the method that we introduced. We were able to then evaluate it on sort of 3 different settings. We took the RoboCup simulator that I've shown you, the one here on the right, transferring it to the real now robots. We also have another sort of intermediate simulator, the gazebo simulator, and we can transfer from gazebo to the real robots, or to get lots of data, for validation purposes, we can transfer from simulation to the other simulation, pretending the new other simulation is the real world, but they still have different dynamics. So we applied this grounded action transformation to learning these fast bipedal walks. We started with what was the fastest walk on these robots, generated by some colleagues at the University of New South Wales, and then we used a policy search algorithm, CMAES, to learn the walk in the simulation, and this is what happened. So the initial policy, like I said, this was the fastest known stable walk on the robot at the time. This was not developed by us; it was developed by the UNSW folks, and it goes about 19.3 centimeters per second. And then we went through an iteration of grounded simulation learning. And after the first iteration, got to this policy, which you'll see is sort of noticeably more squat to the ground, moving the legs a little faster. It's going 26.3 centimeters per second. We then took data from that walk, regrounded the simulator, and did a second iteration, and ended up with this walk, which was at the time the fastest known stable walk on the robots, going 28 centimeters per second. And so that's the sort of the summary of the method, grounded simulation learning. The main result is it improved the walk speed of the now by over 40% compared to state-of-the-art walk engines, and it's the fastest known stable walk on the now. And so this again was inspired by this problem in RoboCup of just generating a fast walk on the robots. But now over the past year or so, a couple of years, we've been extending this to other robotics tests and platforms to ask, when does grounding actions work? When does it not? And also, what are some connections to off-policy evaluation and safe learning and reinforcement learning? And so I'm actually going to take a little detour now and give a little bit of without getting going too deeply into it, some hints of this connections to off-policy evaluation and reinforcement learning. So a little bit of math and technical details there, but then I'll pop back up and show some more videos and extensions of this grounded simulation learning. So so especially for those of you interested in reinforcement learning, Josiah Hanna's thesis, PhD thesis, started from this grounded simulation learning, but that included a lot of research motivated by it on off-policy evaluation. And so how is this connected to grounded simulation learning? The idea is that we're trying to learn a policy that works in the real world, even though the real world is different from the simulator. And so there's a sort of a mismatch between where we're learning and where we're executing. And that's the same case for off-policy reinforcement learning, where you want to try to learn about one policy based on data from executing another policy. And so the general setup is that there's some policy pi, you're trying to learn the value of that policy. What is the value? It's the expected sum of rewards where over trajectories, H, where the trajectories are drawn from by executing this policy pi in the environment. And so the policy evaluation problem is given some target policy pi, and only data generated from a behavior policy pi b, you want to estimate the value of pi. So an example I often give is if you've driven to work along hundreds of different routes, but now you want to take a new route to work from your home. You've never driven it before, but you want to estimate how long it'll take based on how long the other your experience you have from driving the other routes. So when we do this, we're going to estimate our value of this target policy pi. We'll call our estimate b hat, and we'll measure our performance based on how close we get our estimate, the mean squared error of our estimate compared to the actual true value of the target policy pi. So one of the workhorse methods for doing this is known as importance sampling, wherein you reweight the total for the trajectory in your observed data. So you have trajectories H that were drawn from your behavior policy pi b. You want to say how good are those in your target policy pi, and you answer that question with the following equation. You take the total reward that you got from the trajectory in your behavior policy, and you reweight it by the relative likelihood of executing that sequence of actions in your target policy compared to in the behavior policy. So if there's an event that's very rare in your behavior policy but more common in your target policy, then you want to upweight the likelihood of that trajectory. And then you'll average the weighted these weighted totals across all the trajectories you have from your data. So without going too deeply into the technical details, there's two myths of importance sampling, or maybe open questions that we addressed in this research in a series of papers in ICML. The first is that it's actually stated in the Sutton and Bartow reinforcement learning book that off-policy evaluation is sometimes a necessary evil. That if you have access to your true target policy, that you should just use that to gather data, and that will be the best source of information for evaluating how good this target policy is. In other words, if you want to figure out how long it takes to drive from work using a particular route, just drive that route. Don't bother driving other routes. And that seems intuitive. That seems like if you can, then gather data from the policy you care about. But it turns out that that's not the case. Running a behavior, and it's not too hard to see this, and it was known in some of the statistics literature, but it really wasn't sort of connected to the reinforcement learning importance sampling. It's that it turns out that running a behavior policy different from than the target policy can minimize the variance of importance sampling estimates. And when you minimize the variance, you can learn with less data. And it's the intuition behind this is that if there are rare events in your in the policy you care about, actions that you almost never take, it will take a long time to see their effects. If you run the policy you care about, you're better off upweighting those, getting to see what happens in those cases, and then reweighting them using importance sampling. And it turns out that in theory, if you know the target policy and behavior policy, you can actually get a zero variance estimate in just a single trajectory, which motivated us to introduce an algorithm that will help find a behavior policy that gives lower variance importance sampling estimates. We call it behavior policy search. And so we introduced this in the ICML article, and there's lots of empirical results behind this that you can see there, that it really works well. The other myth that we debunk is that if in the importance sampling ratio, I said you take the relative likelihood using your target policy and your behavior policy, it turns out that the myth is that if you know your behavior policy, you should use that to compute the denominator of the importance weights. And again, that turns out to be false. That that even if you know your behavior policy, if you replace the true probabilities of taking actions with the maximum likelihood estimate of the policy that generated the data, that will lower the variance of your importance sampling estimates. So the idea is if you know that you are flipping a fair coin in your as your behavior policy. So in principle, there's a 50% chance of heads and a 50% chance of tails. But in your data sample, you saw 7 heads and 3 tails. You should pretend that fair coin was actually a biased coin with 70% chance of heads. And we prove that using this estimated behavior policy has asymptotically lower variance than using the true behavior policy. Again, something if you're doing off-policy policy evaluation, you can substitute in this method for free, and it's always better. And again, we show a lot of data in our papers. So that's the detour. I hope that was interesting to some of you who are interested in the details of reinforcement learning. For those of you who got a little lost in that section, that's perfectly fine. I'm now going to pop back up to very briefly, some recent extensions to this grounded simulation learning, things that are 2 papers that appeared in last year's IROS, right? This year's IROS is going on right now. But in last year's IROS, along with Haresh Karnan, Sid Desai, Josiah Hanna, and Garrett Warnell, we answered 2 questions about grounded simulation learning. First of all, well, I'll show the video that, again, we replicated the, made sure the results that I showed you previously are weren't a fluke. That we have the robot below that's using the grounded policy, and the one above that's using the original policy, and still using that as a starting point as our baseline for these experiments. And then we looked at the method that I just already explained to you, that basically learns this forwards dynamics model and the inverse dynamics model and composes them. That's essentially trying to make every single action match the effects in the real world. But really what we care about is that the trajectories in the simulation match the trajectories in the real world. And so we sort of reframed this problem in this research as being is learning an action transformer end to end, not by composing the forwards dynamics model and the inverse dynamics model. And then changing the agent environment interface so that we're actually treating this action transformer as the learner. And the goal is for it to learn a function that changes an action to a transformed action that leads to trajectories that are the same in the simulated environment as in the real world. And so this becomes a delayed reward kind of problem. And so now it's a reinforcement learning problem itself, where we still have a forwards model and we use that to generate the reward signal, or the loss function for our action transformer, compared to what trajectories we actually see when we use this. And so we did some experiments in Majoko domains. I'm not gonna, I think for interest of time, I'm not gonna go into the details of them. We basically, we showed that if we use this RGAT, reinforced GAT, as opposed to our original GAT, if we make the simulated and the real world and the simulator exactly the same, you would expect to learn an action transformation function that's the identity. And RGAT allows us to actually do that, whereas GAT has a lot more noise in it. And there's some analysis in our paper about this. And we also showed that if we make the pendulum in these Majoko domains either twice as heavy or twice as light, we get exactly the kind of transformed actions that you would expect to be able to reach to replicate the performance in the real world that we see in the simulator. The other extension was that we looked at transformation to stochastic domains, motivated by this problem where there's unmodeled effects such as bumps in the ground. Here we put foam underneath the carpet that the robot's not able to model, and show that it's that can cause big problems for the robot. And we realized that this is partly because of the way we framed the original grounded action transformation function. It assumed that every action creates a deterministic transition. But in practice, actions could give probabilistic transitions. So if we extend our method to be able to actually learn action transformation functions that are stochastic, that allow for probabilistic transitions of actions, we can get a more robust policy. And in fact, we show that repeating the grounding steps that I showed before, if we use the stochastic version of our algorithm, it doesn't follow. It's able to learn a little bit. It ends up a little bit slower than the original one on flat ground, but instead of falling 6 out of 10 times and then 10 out of 10 times in its trials, it rarely falls. And you can sort of see that here, where on the left we're using the stochastic version of the algorithm, and on the right we're using the original version of the algorithm. Very quickly, the one that's not modeling these probabilistic effects has trouble, and the other one is able to do much better, not perfectly, but is still much more robust. So those were some of the extensions of this grounded action transformation method. Okay, so in the time I have remaining, I'm going to do a talk now, transition from humanoid robots, stay with the theme of machine learning for robot locomotion, but I'm going to change to a different thread of work on wheeled robots called Adaptive Planner ParameterLearning. And this is joint work with especially Zhuishu Zhao and Garrett Warnell, but also several other students as listed at the bottom there. And the idea is it's trying to find a sort of the right medium between classical motion planning, which is not adaptive but can be very robust, and machine learning methods, which are adaptive but tend to not perform nearly as well. so to do that, I'm going to actually change screens to my other computer, because this actually works better on a Mac. So there we go. So the motivation of Adaptive Planner Parameter Learning is that we're deploying an autonomous navigation system in some new environment. And that's, if you've ever tried to do this, it's not as straightforward as it might seem. But people can really do this effortlessly, even non-experts. And so here's Bo Liu, who's a PhD student in my lab, remote controlling a jackal robot, and he can do this without any trouble at all. There's a sort of an obstacle course here, a minefield that it has to go through without touching anything. And he's using, just walking behind the robot, using a game controller. He can steer it through these, this tight corridor. He can steer it away from the obstacles. There's no problems at all with him being able to navigate the robot. So the question is, can we get more robust performance out of existing navigation systems using limited human interaction and learning? So and so a typical classical motion planner will have that comes, for instance, with the robot operating system or ROS move-based navigation stack that takes a lot of inputs. It's a very complex function. It has a lot of parameters, and it'll take it as input the map, the sensors, the odometry. It'll output the actions, and we'd like to be able to not replace the entire classical planner, because it has a lot of properties like guaranteed obstacle avoidance and some and robustness and things, but we want to try to figure out how to again wrap that as a black box and learn parameters that will make it work as effectively as possible for the current environment that we're in. And so AppleD, which is Adaptive Planner Parameter Learning from Demonstrations, it uses behavior cloning to tune a navigation stack. So think of this function G as taking in as being your classical motion planner that's parameterized by a set of parameters theta. It takes in sensor data, it outputs a motor command. It's much more complicated than, it's the complicated thing I showed you on the previous slide. And the question is, what parameters theta do we want to set? And these parameters tend to be things like what's the maximum velocity in the x direction, and the min, and the angular velocity, and there's a whole bunch here that you probably don't, can't even tell what they are. Inflation radius of, how big do we pretend, how much do we pretend the obstacles are bigger than they actually are, things like that. And so we want to try to, rather than manually tune these parameters, which is very time consuming and requires expert input, we want to use behavior cloning to learn these parameters from a demonstration using supervised learning. So we're going to find the best parameter set theta that minimizes the loss function of how close it is to what a person would do. So the rough procedure is we collect a demonstration of states and actions from a person joysticking the robot, and then use black box optimization to solve for these planner parameters. One challenge here is that people exhibit qualitatively different navigation behaviors in different environments. So, in this, in the blue, in the curve versus the obstacle field versus the narrow corridor, people either drive the robot more quickly or more slowly and more carefully. And so it's not that there's a single set of optimal parameters theta star, but rather we want to learn, there's a collection, and we want to be able to learn a context. So we want to find out what's the set of optimal parameters for the current context that you're in. And so we'll use supervised learning also to train a context predictor that says, when you see lots of obstacles nearby, you want to use this parameter theta. When you're in an open area, a different set of parameters. And so when we deploy it, then we use this model. We use this B, which is the context predictor, and then for that context, we output the parameters theta, and then feed them into the classical planner and use that to control the robot. And so in experiments, we use this clear path jackal. We take Bo Liu, one of the authors, using an Xbox wireless controller, navigating through this environment that I already showed him doing. If we just use the parameters that come with the robot, you get the behavior on the left. That it's you know, it doesn't do very well. It has to back up. It can't deal with these narrow corridors. They've given it a set of parameters that is much better tuned for open space. And so once we deploy, you can see the difference very clearly between the learned behavior on the bottom, which is able to sort of change its parameters and appropriately speed up or slow down based on the context, versus the default parameters on the top, which get get stuck quickly, move much more slowly. They don't have collisions, but they're not nearly as effective. And so we're able to show that the traversal time of our AppleD method, which is shown in green, both the behavior cloning loss and the traversal time is significantly better than the alternatives, especially when we use this context predictor. And one of the nice things is that we could use this not just on this single robot. We also tried it on the other robot, the one I showed you earlier in the talk, where we have default on the left, some manually tuned parameters on the right, in the middle, and learned parameters on the right from a single demonstration. This worked just the AppleD method right out of the box, learns to have a much straighter trajectory than using the manually tuned or default parameters. So the idea here is that that was learning from demonstration. We've now generalized this adaptive planner parameter learning method in a series of papers at ICRA and IROS, where to show that we can use not just demonstrations by a person, but also interventions, where a person is watching the robot, but only intervenes when the robot does something wrong. Maybe if it makes a mistake, these are red interventions, or if it just it goes a little too slowly, these are the yellow interventions. But the person leaves the robot alone otherwise, we show that can be an effective interaction modality. We also try evaluative feedback, where a person only has to give either effectively a thumbs up or a thumbs down, basically qualitative. The person doesn't ever control the robot, but just gives this feedback of good job or bad job. That's AppleE. And then we can also use this with a pure reinforcement learning method, where we have to gather data in the simulation in this case, but where we are not learning an end-to-end policy like a behavior controller from scratch, but rather learning the parameters that go into the classical planner and on a sequential step-by-step basis. And we call this AppleR, Adaptive Planner Parameter Learning from Reinforcement. And for that, we introduced a open source data set for these tight navigation problems, where there's environments that range in difficulty from almost wide open to very cluttered. We have 300 different environments that were generated automatically, and we show that the robot's able to learn to navigate through these. And where this is going, this is actually led by a current postdoc in my lab, Shui-Su Zhao, who's about to be faculty at George Mason University starting next year. And the idea is that now we can take all of these methods, the Apple from demonstrations, from interventions, from evaluative feedback, and from reinforcement, and integrate them into a single learning system in the field. And this is sort of more of the vision than this is still ongoing work. But the idea is that you could use the reinforcement AppleR at first back in the factory, then deploy it into a person's home, and use the demonstrations, interventions, and evaluations to tune in your in the deployment setting. And so this is more conceptual. I'm not going to spend any time on this. So but we're trying to get this working with not just the Jackal robot, with other robots as well. And like I've said, we've had good success with that. Okay, so let me stop sharing there and go back to the original presentation. So again, this was the method. This was with Shui-Su Zhao and Garrett Warnell, who's at the Army Research Lab. This idea of adaptive planner parameter learning, where the key idea here is that we're not learning end to end. We're also not just using a classical planner. We're learning the parameters of a classical controller and making them context dependent, and getting much better performance out of the robots. Okay, so with that, I know I'm just about out of time. Just a reminder, my main research question is, to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? I've given you an sort of an overview of some of the things that motivate me, but then also a little bit of a deep dive into some of the particular focus areas that we've worked on recently. I have also worked in other areas of reinforcement learning from human interactions, using advice and demonstration in other contexts. We do a lot of work in transfer learning, and more recently automatic curriculum learning for reinforcement learning. We've used reinforcement learning in other applications, such as musical domains with my former student Elad Liebman, and other robotics domains, and also using some work of my former student Matthew Houseknecht on deep reinforcement learning in continuous action spaces. I haven't really in this talk gone into a main area of interest for me, which is another main area of interest, which is multi-agent systems. I gave sort of some teaser about the autonomous traffic management work we've done. We've also done a lot of work in the trading agent competition. And then the challenge that I'm most excited about these days is what we call ad hoc teamwork. And so just as a one-slide introduction there, you're not going to get the details with it. You'll have to go to my web page to learn a lot more about this. But we've set the problem for us of trying to create a good team player in a multi-agent system, where a good team player is one that's just an individual that has unknown teammates programmed by others. Those teammates are likely to be suboptimal, and we don't have control over them. We can't change them. Instead, we can only change our own behavior to adapt to our current teammates. The kinds of things that I do if I go and play a pickup soccer game with people that I've never seen before. I'm going to play in a different way if I'm playing with people who are all better than me than if I'm playing with people who are the same level as me, for example. People are very good at this. We'd like to get robots to be good at this too. If there's a disaster rescue scenario and I bring a robot and you bring a robot, Robbie brings a robot, and Robin Murphy brings a robot, we want them all to be able to work together seamlessly without us having to reprogram them. And so to do that, they'll have to have not only awareness of their own capability, but ability to quickly model the capabilities of their teammates and figure out, given those capabilities, what actions to take. And we introduced this as a challenge problem at AAAI more than a decade ago now. There have been some theoretical ways to address this using repeated games and game theory and K-armed bandits. We've looked at it from a perspective of sort of birds flocking and thinking of that as an ad hoc teamwork problem. We've also done even RoboCup experiments where we do drop in, pick up robot soccer games where I have to create a robot that's going to be able to play soccer with teammates generated by or programmed by other teams where they don't get to practice ahead of time. And there's now a community around this, some workshops and special issues and survey articles about ad hoc teamwork. So again, that could be the subject of a full talk, but I don't have time for that today. Instead, I'll just summarize that today I focused in on machine learning for robot locomotion, especially grounded simulation learning and adaptive planner parameter learning. My high-level research question is repeated here. And basically I motivated this through RoboCup, the Robot Soccer World Cup. Again, I encourage you all to participate in that. It's a huge inspiration for new challenge problems, new and current challenge problems. And there's a lot of really, there's a great community as well. And then I talked about both grounded simulation learning in humanoids with connections to off-policy reinforcement learning and adaptive planner parameter learning for wheeled robots. And with that, I will be happy to stick around and take any questions you might have.
Great. So thank you, Peter, for a great talk. There have been a bunch of questions that people have already posted in the Q&A panel. But before that, I had one quick question for you. This whole action transformation idea, right, assumes that the dynamics are constant between the simulation and the real world, and then you could just, whatever the differences in the dynamics, you can adjust for it by just changing the actions.
That's right. So yeah, the assumption is that first of all, the dynamics are different. So the dynamics are, you'll never have a simulation that perfectly models the dynamics of the real world. That they are constant, that's true, that they don't change, so that the simulator and the real world are, sort of fixed for the purpose of this learning or throughout this learning process. And then that there are actions, not necessarily that will perfectly, so it turns out we don't get a perfect action transformation function because as maybe you're suggesting, it might be that there are no actions that can get you exactly to the same dynamics of the real world, but we can get closer. And as long as we get closer, which is what will happen during the, sort of the learning process of the grounding function, that the learning should be more effective or work better. And in fact, yeah, when we some of the theory we did for the stochastic case was exactly motivated by the intuition that if we're learning a deterministic action function, that there are many domains where you can't possibly perfectly model the or change the dynamics using the action transformation function because it's a stochastic environment. And so that's why we augmented the class of action transformation functions and found that to be more effective. But yes, you're right. Even so, it's probably never going to be, it's never going to be perfect. And we do have some data showing that it's not perfect. It actually doesn't learn to make the transitions perfectly. But as long as it's better, it should make the learning in simulation more representative of what happens in the real world.
Sure. So let me read out a few questions on at least those that I think are. So Vijay had this question: can we learn transferable skills from low fidelity and highly abstractive environments like circles passing a football around, like in the video, to comparatively difficult environments that simulate at the level of control of robot joints and motors? Yeah,
that's a fantastic question, and it's one that I've thought about a little bit with, but we haven't. I think that we haven't made enough traction on it to write anything or publish anything about it. That's something that I'd encourage pursuit of. I think it is. One question is, could we, can you go through a series of simulators, from a very abstract simulator to a slightly less abstract simulator all the way up to the real world, and that might be more effective than trying to go straight from fully abstract to a fully robust. I think you do need, you probably do need some, but you'd have to then figure out, what's the difference between the effects of your passes in the very abstract simulator versus in the real world. If your simulator, says every time I pass the ball to my teammate, it gets there with 100% probability, but in the real world, when you try to kick the ball to your teammate, some of the time you fall over, some of the time it sprays to the left, some of the time it sprays to the right, you're going to need to then change the simulator so that when you say pass to my teammate, some of the time you actually deliberately kick the ball off in these different directions. And I think that would be the way to use our philosophy or our methodology in that kind of problem that you're bringing up. I think it's a fantastic problem. It'd be a great research direction to pursue. I don't know whether it will work or not. It's an open question.
There's another question here. What exactly was the definition of the stability of these robots? Is it defined by the extent of pitching and rolling of the body, or is it just whether it falls over or not?
So the only metric we used to evaluate was the speed. How the forwards x, I guess it was the y coordinate speed, how fast it moves across the field. We didn't explicitly include stability in the evaluation function, but if the robot fell over, it had to take time to get up, and that would make it basically a disastrous trial. So stability, from that perspective, really, stability was really a binary thing. Does the robot fall over or not? Now, if it's you could change the objective function to make it so that you add something that's looking through the camera of the robot and seeing how much wobble there is, or how much a fixed landmark moves around in the camera. We've done that before for learning when we've used a learning method on the IBO robots for quadruped locomotion back in 2003, Nate Cole's work. It was then followed up by another student of mine, Manish Sagar, who added a part to the evaluation function to explicitly control for stability. And as you'd expect, we learned walks that were more stable but slower. Because now it wasn't just trying to optimize speed. But yeah, in the work I showed today, we were only trying to optimize speed. We didn't add stability as part of the evaluation metric.
So, but and the fact that it learned the more squattish, like the squatting walk, that just came out of the speed and not because it was trying to be stable.
That's right. That's
Wow.
right. It was
Okay.
not. Yeah.
That's amazing.
Now, if it learned, yeah. So if it would, if there was a walk that was faster but fell over 10% of the time, it would prefer the stable walk that never falls over, right? Because those 10% of the time would activate during the evaluations. But yeah, I actually think that the being more squat to the ground was actually advantageous purely from the speed perspective.
Oh, wow. Okay. So I'm not 100% sure about the next question, but I'm trying to paraphrase it. I think he's asking if there's a lot of sensor noise when you're gathering the data, not necessarily in the dynamics, right? So how would that affect your problem?
Yeah. So for the grounded simulation learning case, we are using proprioceptive sensing. So the robot's basically using its proprioceptive sensors to know what joint angle it's at, and it's pretty noise free. It's when the joint's at 90 degrees, there might be a little bit of wiggle in what the proprioceptive sensor says the joint is at, but it's a good question. What would happen if the proprioceptive data were much noisier? We have not, there's noise in the action, in the dynamics function, that's for sure, and we model that explicitly, but in the perceptions, we did not. In this problem in particular, there wasn't really that much noise, so we use the clean sensing. That's another good direction for investigation, is what would happen if the sensor inputs were noisy as well. I don't know.
Okay. So do the panelists want to ask any questions? They can unmute themselves and ask the question, because the panelists can't access the Q&A panel on Zoom. Okay, so if there are no further questions, really thank you, Peter, for this great